Imagine a giant eye in space peering into the cosmos. This eye is the James Webb Space Telescope, or JWST for short. It's the biggest and most powerful space telescope ever built. JWST is like a time machine, seeing light from the earliest stars and galaxies. This light has been traveling for billions of years. JWST is a marvel of human ingenuity, designed to answer some of the biggest questions about our universe. How did the first stars form? Are we alone in the cosmos? These are just some of the mysteries JWST will help us explore. The launch of JWST marks a new chapter in space exploration. Scientists and engineers from 14 countries worked together to make JWST a reality. It took over 20 years and $10 billion to build, but the potential discoveries are priceless. JWST is more than just a scientific instrument. It shows what we can achieve when we work together. As we gaze into the depths of space with JWST, we're also looking into our own potential. The universe is vast and full of wonders. With JWST, we're one step closer to unraveling its secrets. Let's talk about size. JWST is big, really big. Its main mirror is 6.5 meters across. That's almost 3 times bigger than Hubble's mirror. JWST's sunshield is about the size of a tennis court. The bigger the mirror, the more light it can collect. More light means JWST can see fainter, more distant objects. It can peer further back in time, almost to the beginning of the universe. Hubble mainly sees visible light. JWST is designed to see infrared light. Infrared light can pass through cosmic dust clouds. This means JWST can see things hidden from Hubble's view. Together, they give us a more complete picture of the universe. At the core of JWST is its revolutionary technology. The heart of the telescope is its primary mirror, made up of 18 hexagonal segments. Each segment is beryllium, coated with gold. This helps reflect infrared light better. Each segment can be adjusted independently. This flexibility is crucial for unfolding in space. Another key technology is JWST's sunshield, about the size of a tennis court made of captain. It protects the telescope from heat and light, keeping the instruments extremely cold. JWST also has advanced detectors, capturing and analyzing faint light. All these technologies make JWST a powerful tool, a testament to human ingenuity and collaboration. JWST's design is a masterpiece of engineering. It had to be folded up to fit inside a rocket and then unfold itself in space. This process is like a cosmic origami. The unfolding took about 2 weeks. The first thing to unfold was the solar array. Next came the sunshield, like a giant parasol. It has 5 layers, each thinner than a human hair. Then, the secondary mirror unfolded. Finally, the primary mirror unfolded like flower petals. Now fully unfolded, JWST is ready to explore the universe. Its innovative design allows it to peer further into space, a tribute to the hardworking engineers. One of JWST's coolest tools is the coronagraph. It's like sunglasses for the telescope. A coronagraph blocks out the bright light from stars. This lets JWST see fainter objects nearby, like planets. Imagine trying to see a firefly next to a bright spotlight. The star's light drowns out the planet's faint glow. The coronagraph solves this problem by creating an artificial eclipse. It blocks the star's light, letting the planet shine through. This is crucial for studying exoplanets, planets around other stars. With the coronagraph, JWST can directly image exoplanets. This means taking actual pictures of worlds beyond our solar system. It can study the atmospheres of these distant planets. This could help us find signs of life. The coronagraph can also study disks of dust and gas around young stars. These disks are where planets form. The coronagraph is a game changer for exoplanet research. It allows us to see things we've never seen before. We can study planets that were once hidden by their star's glare. This tool opens up new possibilities for understanding how planets form and evolve. JWST has another powerful tool, spectrographs. These instruments are like cosmic code breakers. They split light into its component colors, creating a spectrum like a rainbow. But this rainbow tells us a lot about what we're looking at. Spectrographs help us understand the chemistry of distant objects. Every element and molecule has a unique spectral signature. It's like a fingerprint made of light. When we look at a star's spectrum, we can see what it's made of. We can tell its temperature and age. For planets, we can study their atmospheres. We might even detect signs of life. Spectrographs turn light into knowledge. JWST has several types of spectrographs. One is called a no-slit spectrograph, which can look at many objects at once. Another is a near-infrared spectrograph, perfect for studying the oldest and most distant galaxies. There's also a mid-infrared instrument that can peer through cosmic dust. These spectrographs work together to give us a complete picture. They can study everything from nearby planets to the earliest galaxies. They help us understand how elements are spread through the universe. Spectrographs are like JWST's eyes and ears, helping us listen to the stories that starlight tells. JWST isn't orbiting Earth like many other satellites. It's much farther away, about 1.5 million kilometers or 1 million miles from Earth. That's about 4 times farther than the Moon. The answer lies in a special place called the second Lagrange point, or L2. L2 is a spot where the gravity of the Earth and Sun balance out. This creates a stable location for JWST to orbit. At L2, JWST always keeps Earth between it and the Sun. This is crucial for its mission. JWST needs to stay very cold to detect faint infrared light. Being at L2 helps it stay cool. JWST can see a large part of the sky at any time. It doesn't have to deal with Earth getting in the way. This means more efficient observing time. JWST can look at the same spot in the sky for long periods. This is great for studying faint, distant objects. However, being so far away has challenges. We can't send astronauts to repair JWST like we did with Hubble, but the benefits outweigh the challenges. JWST's mission is ambitious. It aims to answer some of the biggest questions in astronomy. One goal is to see the first stars and galaxies that formed after the Big Bang. These objects are so far away that their light is very faint. JWST's large mirror and sensitive instruments make this possible. It's like looking back in time to the cosmic dawn. Another key mission is to study exoplanets. JWST can analyze the atmospheres of planets around other stars. It might find signs of water, methane, or other molecules. These could be clues to the presence of life. JWST can also study how planets form. It can look at disks of dust and gas around young stars where planets are born. JWST will also study objects closer to home. It can look at planets and moons in our own solar system. It can peer through the clouds of Saturn's moon Titan. It might spot icy plumes on Jupiter's moon Europa. JWST can even study comets and asteroids. The mission isn't just about specific targets, it's about discovery. JWST is so powerful that it's sure to find things we never expected. Each day of its mission brings the potential for new cosmic revelations. JWST's journey to space was long and challenging. The project started in 1996, but it faced many delays and setbacks. The telescope was much more complex than initially thought. Its budget grew, and the launch date kept getting pushed back. Many wondered if it would ever fly. But scientists and engineers persevered. One of the biggest challenges was testing. JWST had to work perfectly the first time. There's no way to fix it once it's in space, so every part had to be tested rigorously. The mirror segments were tested in extreme cold. The sunshield was unfolded and refolded many times. Engineers simulated the vibrations of launch. They even tested how JWST would communicate from far away. Finally, on December 25, 2021, JWST launched. It was a tense moment for everyone involved. The launch went perfectly, but the mission was far from over. JWST had to unfold itself in space. This complex process took about 2 weeks. Each step was crucial. If anything went wrong, the whole mission could fail. But JWST performed flawlessly. JWST is more than just a new telescope. It's a revolution in astronomy. It's changing how we study the universe. JWST can see things that were invisible to previous telescopes. It's like giving astronomers a new pair of eyes. These eyes can see further and clearer than ever before. This opens up new possibilities for discovery. One big change is in the study of exoplanets. Before JWST, we could detect planets around other stars, but we couldn't study them in detail. JWST can analyze the atmospheres of these distant worlds. It might find signs of water, oxygen, or even life. This could answer one of humanity's oldest questions. Are we alone in the universe? JWST is also transforming our understanding of cosmic history. It can see the first galaxies that formed after the Big Bang. This helps us understand how the universe evolved. We can trace the growth of galaxies over billions of years. JWST might even help solve the mystery of dark matter and dark energy. For astronomers, JWST is like a time machine and a magnifying glass combined. It's opening up new fields of study. JWST is just the beginning. It's paving the way for future space telescopes. Scientists are already planning the next generation of observatories. These will build on JWST's discoveries. They might focus on finding the future of space exploration is bright.